So a good example of an RC circuit is the diagram below. So what we have is we have a battery. We have a switch, which gives us the ability to open and close the circuit. We have a resistor, and we have a capacitor. And we want to know what happens to the change in voltage across the capacitor after the switch has been closed for a very long time. So what happens is once this switch is closed, it's going to complete the circuit. All of this charge in the battery, which we're calling epsilon, that entire voltage is going to go to the capacitor. So the change in voltage across the capacitor is going to be equivalent to epsilon, whatever this voltage is that was in the battery. All of it's going to leave. We're also going to look at what is the maximum charge in terms of epsilon, R, and C. To determine this, we simply just need to look at the equation that Q max is equal after the circuit's been closed, right? After t approaches infinity. So all of this is ranging on the fact that a lot of time has passed. The maximum charge is actually equal to the capacitance times that voltage that was in the battery, so epsilon. And in terms of figuring out if the current is positive or negative in the circuit, we really simply need to say what's happening with the charge. And because we're taking the charge from the battery and charging up the capacitor, we have a positive circuit. So it's positive because we are charging up the capacitor. Now let's look at, we want to find an expression for current and time, and we want to graph it as t goes from 0 to t goes to 5 tau. And so to better understand this, there is an equation for current that is equal to this voltage in the battery over the resistance times e to the negative t over tau. Okay? And the way we're going to charge this, since we are going from time 0 to time 5 tau, we can represent this in terms of x's and y's, right? And to do that, I'm actually going to reform the equation. I'm going to say, well, let's say I divided by epsilon over r, I'm just going to move this to the other side, is equal to e to the negative t over tau. And this might look even less simple, but you'll see what I'm going to do here in a second. Because I'm going to graph this in Desmos, I'm going to put it in terms of y and x. So let's let y equal our current divided by our battery voltage over the resistance. And let's let our x equal our t over tau. And what this is going to do is when I have a t that equals 0, this whole exponent is going to go to 0, which is going to make this side just go to 1, because anything raised to the 0 power is 1. And when I have t equaling 5 tau, the exponent is just going to go to 5. So you're going to see what's going to happen, because we don't want to forget that that exponent's negative. But let's go over to Desmos and graph this real quick. So I said my y was the current over the battery voltage over the resistance. So I'm just going to say that that's equal to e raised to the negative t over tau, which we're just representing as x. So negative x. And this is actually a perfect example graph of what this equation is actually going to look like and how that current changes over time.